All right, 2.6, graphs of rational functions. Yes. All right, so we're going to look at the definition of rational functions. I already spent 3 days on that other section. We'll go over it tomorrow once the homework is due, because I'm not just going to do all your homework for you. Let f and g be polynomial functions with g of x not equal to 0. Then the function given by r of x is equal to f of x over g of x is a rational function. So these problems kind of go back a little bit to finding the domain of the functions. So if you were to have something like where's there a t? Oh. So we're going to find the domain, then use the limits to find end behavior at the value or values of x not in the domain. So let's just say we have something like f of x is equal to 2 over x minus 3. At what values does this not exist, or what values are not in the domain? How do I find them? Nope. Nope. 3. Okay, so you set the denominator equal to 0. So x minus 3 is equal to 0. So when x equals 3, okay, that is undefined. So our domain from negative infinity to 3 union 3 to infinity. So we're including everything except for 3. Okay, going back to asymptotes. Where is our vertical asymptote? How do we get a vertical asymptote? Yes. X equals what? Okay, a lot of people are saying this one. So what's the horizontal asymptote then? Okay, remember your clown poem. So then what's the vertical asymptote? Clown poem goes with the horizontal. Yes. Not the asymptote. We talked about domain. So a vertical asymptote occurs when the denominator is equal to 0. Okay, that's the way we have a vertical asymptote. So that means that when x is equal to 3, okay, basically the graph does not exist there because it's not in the domain. So that is the domain. This is just kind of a review of asymptotes and stuff from before. Okay, but then it says it wants us to use limits to find the end behavior. Okay, so with this, it says that it wants us to use the one for whatever this value is. So we have the limit as x approaches 3 from the left of f of x, and we're going to look at the limit as x approaches 3 from the right of f of x. So, as I get really, really close to 3, okay, what's happening from the left side? So if I were to put like 2.9 here, what's happening? For x. That's not what I want to know. What's happening to y as x gets really, really close to 3 on the left side? What's happening to y? Bigger? Smaller. This number is going towards infinity. So, negative infinity, I should say. Negative infinity. Okay? How about let's look at it if I did... What's happening to the other one as it goes to 3 from the right? Big, big number, so it's going toward infinity. Okay, a good rule of thumb is if you have a number here for the limit, the whole thing's going to either infinity or negative infinity. If you have an infinity here or a negative infinity, oftentimes it's going to a number. Okay, not all the time, but oftentimes. Alright, so quickly with vertical asymptotes, okay, we're looking at end behavior. The vertical asymptote is x is equal to a. So the limit as x approaches a from the left of f of x is equal to positive or negative infinity. And the limit as x approaches a from the right of f of x is equal to positive or negative infinity. Okay, so that's for vertical asymptotes. So that's the situation we were dealing with here, okay, when we checked the end behavior at that point. But the other option, we can also check it at a horizontal asymptote, which is y is equal to b. So then we're checking the limit as x approaches negative infinity of f of x, and that's going to be equal to b. Okay, or the limit as x approaches infinity of f of x is also equal to b. Okay, not saying b can't be negative, but it's just equal to b. Alright, so just so you know, there's several problems in the book that tell you to like talk about like the transformations of graphs and stuff like that and how they're shifted. We're not going to actually do that part of it. Okay, I'm not worried about that part, but we are going to do the stuff with the asymptotes. So it'll say like also list like vertical and horizontal asymptotes, find a domain of the function, and talk about in behavior. So basically what we just did up here is what you'll be doing in the problems, not exactly what the instructions say to do. Let's see. Do y'all remember how to find intercepts of a function? Where it crosses the x or y axis. Okay. Really quick, we're going to write down a couple little note things and then we'll look at an example or two. Actually, I might just give y'all time to work on the problems that are due tomorrow. I don't know, but after we do this, we're going to do this one other note thing first, at least. Alright, so, graph of a rational function. The graph of y is equal to f of x divided by g of x, okay, which would be something like a sub n x to the n plus dot dot dot, divided by b sub n x to the, or b sub m, sorry, x to the m plus dot dot dot, has the following characteristics, and there's going to be 4 of them. Okay, with some things underneath each of them. In behavior, asymptote, and there's going to be 4 under here. If n is less than m, the in behavior asymptote is the horizontal asymptote y is equal to 0. If n is equal to m, the in behavior asymptote is the horizontal asymptote y is equal to a sub n divided by b sub m. If n is greater than m, the in behavior asymptote is the quotient polynomial function y is equal to q of x, where f of x is equal to g of x, q of x, plus r of x. Hopefully that looks familiar. There is no horizontal asymptote. So that's all for in behavior. So you have the different cases in, at least there's only 3 of them. In less than m, and equal to m, and greater than m. Vertical asymptotes. These occur at the real zeros of the denominator. So that's just a fancy way of saying when the denominator is equal to 0. Provided that the zeros are not also zeros of the numerator or equal or greater multiplicity then X-Intercepts these occur at the real zeros of the numerator which are not also zeros of the denominator so again, essentially a fancy way for saying where it crosses the x-axis. So essentially to find it, you set y equal to 0 and solve for x. So that's why it wouldn't also be something that's a 0 of the denominator, because the denominator is going to go away. And so lastly, then we have the Y-intercept. It's like it is a little box in the book. This is the value of f of 0 if defined. So setting x equal to 0, solving for y. I'm going to see if I can fit this last thing at the bottom. It doesn't go with this, so I'm going to... If the end behavior asymptote of a rational function is a slant line, we call it a slant asymptote. Or oblique asymptote. Alright, I think rather than doing more examples, I'm going to give you guys the rest of the time to finish the homework that's due tomorrow. And then we can go over any questions you have on it tomorrow.